Hi, everybody. It's Professor Mitchell. Today we're starting Chapter 3 on numeration systems and whole number operations. So in the first section, 3.1, we're going to talk about numeration systems. You will be able to understand and explain numbers, their origin, and their representation in numerals and models, different numeration systems, including the Hindu-Arabic system, and place value and counting in base 10 and other bases. Numerals are written symbols to represent cardinal numbers. So, of course, you're very familiar with the set of numerals on the bottom. These are the ones that we use. Throughout history, there have been other numeration systems that have been used. For example, you've probably seen Roman numerals before. They're still used for certain things, but the other ones are probably not as familiar to you. So through this chapter, we're going to be looking at some of these, and believe it or not, it'll really help you understand our system a little better. A numeration system is a collection of properties and symbols agreed upon to represent numbers systematically. So here's a system that I use, and you probably use it. If I'm trying to count something, for example, how many times did a certain thing come up in a list, I will use tally marks, like you see here, uses single strokes to represent each object that is counted. And to make them easier to count, we traditionally, lump them together in groups of 5. All right, so here's an example of 13 written with a tally system. The Egyptian numeration system used these things that really look like hieroglyphics to represent different numbers. The number 1 was represented by a vertical staff that looks like our number 1. And then 10 was represented using what's called a heel bone. And then other powers of 10 were represented using a scroll, a lotus flower, a pointing finger, a pollywog or burbot, and finally, astonished man. Okay, so we might be looking at that system a little bit more later in this chapter. Next, we have the Babylonian numeration system. It only used 2 different numerals to represent 1 and 10. The Mayan numeration system was kind of what we call a base 5 system. Notice that the Mayans had a numeral for 0, and that's something that a lot of other, earlier civilizations didn't have. And they also had symbols for 1 and 5. The Roman numeration system, again, this is probably kind of familiar to you, used different letters to represent different numbers. The Roman numeration system is also an example of what's called a positional system. So for example, to write the number 6, you write VI, but to write the number 4, you write IV. So there was an understanding that writing the I before the V represented subtraction. All right, and here you see more examples of the positional usage, putting a smaller number before a bigger number to represent subtraction. All right, let's look at some examples of numeration systems, starting with the Egyptian numeration system. So first, we're going to use the Egyptian system to represent 1,312,312. And then we'll use the Hindu-Arabic system, which remember is our system, to represent this number. So we're kind of going in both directions here. So the Egyptian system is pretty simple, other than the characters that you have to learn to draw. And by the way, at least in my class, the numeration systems would always be open notes. You could have a sheet of paper that has all these symbols on it. That's totally fine. I kind of need that myself most of the time. So, but it is a pretty simple system. You just start with the biggest symbol that you need, which in this case would be 1 million, the astonished man. And then if you need more than one of them, you just take however many you need. Okay, so for example, 1,312,312, that would just look like this. So here's the astonished man representing 1 million, 3 of the polywogs representing 300,000, 1 pointing finger for 10,000, 2 lotus flowers for 2,000, 3 scrolls for 300, 1 heel bone for 10, and 2 vertical staffs for 2. And then to go the other way, it's just as simple. So what I did for this one was I started off writing it in expanded form. So since you have 2 of the polywogs, that represents 2 times 100,000. 3 lotus flowers is 3 times 1,000. 3 heel bones is 3 times 10, and then 4 vertical staffs is 4. And that all adds up to 203,034. All right, next we have the Babylonian system. Babylonian is a base 60 system. So this is a little more complicated. All right, so in these examples, we're first going to use the Babylonian system to represent 12,321, and I'll be going to the tablet for that. And then we're going to use the Hindu Arabic system to represent this number. By the way, this is just a period. Okay, so let's switch over to the tablet. All right, so we're trying to do 12,321. So I've set up my base 60 system where the symbols that go under 1 will just represent 1s. The symbols that go under 60 will represent 60s, and the symbols that go under 60 will represent how many times do I have 3,600. All right, so we have 12,321. Now, if I were to continue my table, another place going this way, the next place value would represent 60 cubed. 60 cubed is bigger than 12,321, so I don't need any of those, but I do need to know how many times does 3,600 go into 12,321. Believe it goes 3 times. 3 times 3,600 is 10,800. And I'm left with 1,521. So I have 3 60 squareds. All right, next I need to know how many times does 60 go into 1,521. Well, 60 goes into 152 2 times. 2 times 60 is 120. 152 minus 120 is 32. Bring down the 1. 60 goes into 321 5 times. Whoops. And then 5 times 60 is 300. 21 left over. So the way that we're going to break up this number in the Babylonian system is 3 60 squareds and then 25 60s and then 21 ones. So now I just have to use my symbols to write those numbers, and they just get written from left to right. So, excuse me for 1 second here. Okay. So the way you write 3 is with the 3 inverted triangles, which really should be colored in. How good am I at coloring on here? It's not too bad. And then you leave a space, and then write 25. So the way you write 25 in Babylonian is with the 2 symbols like this that represent tens, and then 5 of the triangles. Babylonian numbers do take up a bit of space. Okay, and then finally 21, skip a space and write down 21. So that would be two of these things and then one of these. Okay, so believe it or not, this is how you write the number 1,521 in the Babylonian system. All right, so now let's switch back. The other thing I don't need the tablet for. Okay. All right, so you just saw letter A. Letter B, I'll just show you right on here. So the two triangles represent 2, and this is in the 60 squareds place. This thing and then the triangle represent 11. This is 10, this is 1. So that's how many 60s you have. And then the very last one just represents 1. So this number represents 2 times 60 squared plus 11 times 60 plus 1, which comes out to 7,861. All right, next we have the Mayan system. The Mayan system is very interesting. It's kind of similar to Babylonian in that it the positions represent certain place values. This almost looks like a base 20 system with one little exception that I'll tell you about. Okay. In the meantime, these are our 3 symbols. Notice that unlike Babylonian, the Mayans did have a symbol for 0. That was very progressive of them. Okay, and then we have the Roman system. So I'll do the Mayan and the Roman just within one example. So you're probably familiar with Roman numerals. We do see them on different things. You know, for example, on old buildings, you know, it will sometimes indicate the year the building was built or something. So in the Roman system, we have symbols for 1, 5, 10, 50, 100, 500, and 1,000. And then the Romans did represent larger numbers than that. For example, we're going to do one example that involves 5,000. So if you want to write 5,000, what you can do is take the symbol for 5 and then just put a bar over it. So putting a bar over a symbol multiplies it by 1,000. Now, what's unique about the Roman system is that they had this kind of subtractive thing going on, where, for example, instead of writing the number 4 with 4, you know, letter I's, they would just put a letter I before a letter V. And they understood that when you saw a symbol for a smaller number before the symbol for a larger number, that meant subtract the smaller number from the larger number. Now, what you might not know is that you're not allowed to do this with just whatever numbers you want. For example, you would not write the number 49 as IL. That was not allowed in the Roman system for some reason. So actually, all of these numbers here are the only ones that you would ever see that subtractive thing for. So I was kind of staring at this a few minutes ago and I noticed, well, no, that doesn't work perfectly either. So never mind, let's just, these 6 numbers are the only ones that you're allowed to write using that subtractive property. Okay, so now to the example. First, we're going to write CCXLIX as a Hindu Arabic numeral, you know, the way that we write our numbers. Then we're going to use Roman numerals to represent these 3 numbers. And then finally, we're going to use Mayan numerals to represent those 2 numbers. Okay, let's get these Roman numerals out of the way first. So first, we're writing CCXLIX as a Hindu Arabic numeral. CC represents 200. And then XL, that was one of the ones that was on the list for the subtractive numbers. That represents 40. So far we have 200, 40, And then here's another subtractive number, ix represents 9. So this number is 249. All right, and then going the other way, using Roman numerals to represent those numbers, starting with 1,634. 1,000 is M. 600 would be 500 followed by 100, so that would be what? DC. So MDC, and then 30 you just write as XXX, and then 4 would be IV, just like this. MDC, so there's 1,000, 500, 100, 10, 20, 30, and then IV is 4. All right, next we have 5,280. So I mentioned to write 5,000, you can take a V and put a bar over it. For 200, you would do CC, just like we did up here. And then 80 would be 50, which is L, followed by 30, which is XXX. So V bar, CC, L, XXX. And then finally we have 88. So that would be 50, which is L, plus 30, which is XXX. And then unfortunately 8, you can't do anything subtractive. You just have to go VIII. So that's what it would be, L, XXX, VIII. All right, that brings us to our Mayan numerals, and I'm going to have to do this on the tablet, starting with 684. Okay, so let me start by telling you about the place value system for Mayan. It's almost a base 20 system. Oh, it's in red, I guess it doesn't matter. Almost a base 20 system. It starts with 1s and then goes 20s. But then in the next place, instead of going 20 squared, it goes 20 times 18. And the reason they did that was 360 is about the number of days in a calendar year. So they did that to help with their calendar, and then they had 5 days that they considered unlucky. All right. But then it goes back to being base 20. So then the next place would be 20 squared times 18. The place after that would be 20 cubed times 18. I don't think we're going to need any more than 3 of these places. All right. So the first number was 684. So I look over my place values and I ask what is the largest one of them that will divide into 684, and it's 20 times 18. Oops. No. So I ask how many times does 360 go into 684? The answer is 1 time, with 324 left over. So I'm going to put a 1 here. Now I need to know how many times does 20 go into 324, right? Okay, well, 20 into 32 goes once. 1 times 20 is 20. 32 minus 20 is 12. Bring down the 4. Looks like 16. 6 times 20 is 120. Sorry, I'm squeezing this in at the bottom. It's just I'm trying to save this space over here for the answer. Okay, so there's a 4 hiding there. All right. Okay, so we need 16 of these, and then we need 4 of these. So the way the Mayans wrote their numbers, they wrote them vertically. So I'm going to start with the 1. The 1 would just be a dot. Oops. And then I'm going to leave a space going down, and I'm going to write the symbol for 16, which is 3 lines. They represent 5 each, and then a dot right above it. So that represents 16. And then 4 would be just 4 dots. Where the 0 would come into it would be if, for example, the number 362 would have one of these, but it wouldn't have any of these. That would be a 0, and then there would be a 2 right there. So 362 would get a dot, and then that eyeball looking thing, which I think looked like this. And then it would get, what did I say, 362, that would get 2 dots. Okay. All right, so that's 684. So the next example was 164, if you want to pause the video and try that one. We got 1s and we got 20s, and I think in this case we are not going to need 20 times 18 because that's bigger than 164. So we're just going to ask, how many times does 20 go into 164? It goes 8 times with 4 left over. So 8 of these and 4 of these. So you would write your symbol for 8, which is a line representing 5, and then 3 dots, and then leave a nice big space going down, and then put 4 dots representing the 4. So this would be your answer. And that brings us to our numeration system, which is called the Hindu-Arabic numeration system. All numerals are constructed from 10 digits, 0 through 9. Place value is based on powers of 10, which is the number base of the system. So of course, for example, the numbers 163 and 361 use the same numerals, but they represent different numbers because the positions of the numbers are important. Okay, not all numeration systems had that. All right, more about place value. Place value assigns a value to a digit depending on its placement in a numeral. So in the base 10 system, the rightmost digit represents ones or units. The second to the right digit represents tens, and the next digit to the left represents hundreds. Notice hundreds, 100 is 10 to the second power. And the digit to the left of that represents thousands. 1,000 is 10 to the third power. And here you see the expanded form of the number 6,789. It takes each digit and multiplies it by its place value. Here again is the definition of exponent. If a is any number and n is any natural number, then a to the power n means a times a times a, et cetera, n times. There are n factors of a. And then anything to the power 0 is 1, except 0 to the power 0 is undefined. All right, exponents are important when you're doing place value. So one tool that's used to help children understand the base 10 system is called base 10 blocks. So you have units to represent ones, you have longs to represent tens, you have flats to represent hundreds, and then you have blocks to represent thousands. So in this example, we're going to trade 11 flats, 17 longs, and 16 units to obtain the fewest blocks possible. This is an exercise that you can do to help children understand the concepts of carrying and addition and borrowing and subtraction. So I start with 11 flats, 17 longs, and 16 units. And what I'm going to do first is I'm going to take away 10 of these units and trade them for 1 long. So see here what happens is 16 units becomes 1 long and 6 units. All right, 16 units is equal to 1 long and 6 units. So after the first trade, we have 11 flats, 18 longs, and 6 units. So that's fewer blocks than we had to start with, but we can do better than that. Now we can take some of these longs and trade them in for a flat. So we take our 11 flats, 18 longs, and 6 units. We're going to take 10 of the longs and trade them in for 1 flat. So 18 longs becomes 1 flat and 8 longs. That leaves us with 12 flats, 8 longs, and 6 units. So that's even better. But we can take it one step further because remember, we also have blocks. So finally, we're going to take our 12 flats. We're going to trade 10 of those flats for a block. And that leaves us with 1 block, 2 flats, 8 longs, and 6 units. And that's the best we can do. That is actually a representation of the number 1,286. Okay, so the fewest possible number of blocks that you can use to represent this number is 17 blocks. I should say pieces. Fewest number of pieces. Yeah, block means something specific. All right. Now, it is thought that the reason we use a base 10 system is because we have 10 fingers. All right. But it's worth looking at other base systems, other number base systems. For example, base 5, which is called quinary, is based on the concept of just doing all your counting on one hand. It only uses the numerals 0 through 4. And then when you get up to what we typically think of as 5, think of that as 1 hand and 0 fingers, and that number is written as 1, 0. All right, so with the units and longs system, think of this as 1 long and 0 units, but this time a long only has 5 units in it. All right, and continuing, be careful not to read these numbers as 10, 11, 12, 13, because that kind of suggests base 10. So I always read numbers in other bases just as 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. Notice 1, 4 is 1 hand and 4 fingers. And then the next number would be 1 hand and 5 fingers, but remember there is no numeral 5 in base 5. So that would be 2 hands and 0 fingers, and that would be written as 2, 0. Another fun way to represent base 5 is with pennies, nickels, and quarters. You can represent base 10 using pennies, dimes, and dollars, dollar bills. I like to use pennies, nickels, and quarters to represent base 5. So hopefully in a future section, I'll have the opportunity to show that to you. All right, so in this example, we're going to convert 11244, base 5, into base 10. So this turns out to be pretty simple, as long as you understand base 5. In the base 5 system, instead of having ones, tens, hundreds, thousands, etc., you have ones, fives, 25s, 125s, and 625s. Notice that those are all powers of 5. So you set up this table. Our number here has 5 numerals in it. I'm not going to call them digits because that's also a kind of a base 10 concept. Fill those in underneath and then write it in expanded form. So this number 11244 in base 5 represents the number 1 times 5 to the 4th plus 1 times 5 to the 3rd plus 2 times 5 squared plus 4 times 5 to the 1st plus 4 times 1, which comes out to 824 in base 10. All right, now you can make you can use any base you want, really. Another common one is base 2. That's called binary. There are only 2 digits, 0 and 1. And this is what computers use because the 0 and the 1 represent 0 sort of represents that a switch is off, and 1 represents that the switch is on. All right. Okay, so very similar to the last example, if we wanted to convert 10111 to base 10, remember now we are in base 2, so our place values are 1, 2, 4, 8, 16, which are powers of 2. And when I put my numerals underneath those place values, I get 1 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 4th plus 1 times 2 to the 1st plus 1, which comes out to 23. Now you can also go the other way. I'm sorry that popped up right away. If I wanted to convert the number 27, which is base 10, our ordinary, familiar 27, into base 2, that is a little more complicated, and I thought that I would show you this on my tablet. I thought it might be easier to follow than what you see here. What you see here is basically long division, but it's written in kind of an unfamiliar way. So I'm going to switch over to the tablet and show it to you the way that I would normally do it. Okay, so let's see. Where is my screen? Okay, so we're trying to convert the number 27 to base 2. So the first thing I'm going to do is set up my base 2 system. And maybe I don't know right ahead of time how many numerals it's going to take to write this number in base 2. So I will start over here with a 1, and then 2, which is 2 to the 1st, and then 4, which is 2 to the 2nd, and then 8, 16. And I'm going to stop there because if I go to 32, 32 is bigger than 27. So I know that to represent the number 27, I'm not going to need any place values 32 or bigger. So the first thing I need to know is how many 16s are there in 27? And so that's just a long division problem. 16 into 27 goes 1 time and leaves 11. So this 1 is going to go here. And now I need to ask how many times does 8, the next place value, go into 11? It goes 1 time. So that 1 is going to go here. The next question would be how many times does 4 go into 3? And the answer is 0. Next place value is 2. 2 goes into 3 1 time. And then 1 goes into 1 1 time. Okay. So that means that to represent the number 27 in base 2, you would write it as 1 1 0 1 1. And don't forget to put the subscript that indicates what base you're in. If I don't see a subscript, I assume it's base 10. All right. So that's what they're doing here. They're doing long division. I thought it looked a little confusing, especially if you've never seen it written that way. All right. Another common system is base 12 called the duodecimal system. That uses 12 digits. So we have to create some new digits that we don't use in our system. So we will use T and E to represent 10 and 11. Base 12, you have 12. Oh, they do call them digits. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2 new digits, T and E. So that takes a little getting used to. All right, converting a base 12 number into base 10 is easy. Just remember that your base 12 place values are 1, 12 to the first, and 12 to the second. It might be helpful, actually, if I switch back to the tablet. They did not show quite as much work on this one. Okay, now let's see. It was E2T, wasn't it? Yes, it was. Okay. All right. So E2T in base 12. My base 12 system has 1s, 12s, and 144s. So whenever you have the digits E or T, it might be helpful to write, a traditional 10 or 11 next to it. Okay, and so this is how they came up with 11 times 10 to the, or 12 to the second, plus 2 times 12 to the first, plus 10 times 1. Okay, and I can't do that math in my head, so let's switch back to this. Okay, so that comes out to 1,618. Okay, let's see. Okay, the next example is to convert 1,277, which is a base 10 number, into base 12. So this is the long division thing that we did earlier with base 2. I am going to switch back to the tablet. All right, so in base 12, you have 1s, 12s, 144s, and 12 to the third. I believe 12 to the third is bigger than 1,277. I'm 99% sure it is. Let me just double check. Yes, 12 to the third is 1,728. So we're not going to need any of those. The first place value we're going to need is 12 to the second, which is 144. So the first thing I want to know is how many times does 144 go into 1,277? The answer is 8. And let's see, 8 times 144, that would be a 2, carry the 3, 5, carry another 3, that would be 1,152. And then the remainder is going to be the next number that I divide 12 into. So I do need that remainder. That remainder is 125. So I know I'm going to put an 8 under here. Next, I need to know how many times does 12 go into 125. It goes 10 times. Okay, but remember that's not how we write the number 10 in base 12. We write it like this. And we have 5 left over. So instead of asking how many times does 1 go into 5, you can just put a 5 there. So that means in base 12, the number 1,277 is written as 8T5. All right. Oops. Okay, so they write it like that. Okay, and for the last example, Rob used base 12 to write the following, the number G36. So please don't panic. G is not another digit in base 12 that I didn't tell you about. It represents a mystery unknown digit that we're going to figure out, okay? So the number G36 in base 12 is equal to the number 1,050. All right, and that is enough information to determine the value of G. So if you just write this mystery number G36 in expanded form, it would look like this: G times 12 to the second plus 3 times 12 to the first plus 6 times 1 has to equal 1050. So now this is just a little easy algebra problem. 144G plus 36 plus 6 is equal to 1050. You combine these like terms, gives you 42. Subtract 42 from both sides, you get 144G equals 1008, which means G must be 7. So the number 1050 in base 10 is equal to the number 736 in base 12. For section 3, we'll see you next time.